Boom. All right, Julian, welcome. This is Dielectrics, yeah, chapter 6. In the former chapter, we were discussing capacitors and we did justice to capacitors. Now we are looking at dielectrics. Good. Before I tell you what a dielectric material is, it is important for you to know that in most capacitors, a non-conducting material is placed between the capacitor plates. And this non-conducting material has two basic functions it performs. Number one, it acts as an insulating material that separates the two parallel plate capacitors from touching each other. And because it prevents them from touching each other, therefore charges are stored. If this material was a conducting material that actually either brings the two plates together, then charges will flow from the positive terminal of the battery to the negative terminal of the same battery without being stored in the capacitors. So that is the number one job a non-conducting material will do between capacitor plates. The second thing it will do is that the non-conducting material will increase the capacitance of the capacitor. No matter the type of material you put, so long as it's an insulator, it will increase the capacitance of the capacitor. And the fact there remains that the dielectric constant of every insulating material is always 1 and above, is greater than 1. It is only equal to 1 when it is in a vacuum. So every non-conducting material has a constant of 1 and above. In fact, it starts from 1 point something to. All right, sorry for that call. I think I had a call, so the call actually interrupted what I was saying. So we are saying that every non-conducting material has a K value of 2, 1 and above. In fact, it's above 1. When it is equal to 1, just know that there is no dielectric material, right? So that is what it will perform again. Very, very important. So in a nutshell, this non-conducting material that you place between capacitor plates so as to separate charges from them flowing into the other side or increasing the capacitance of the capacitor, you refer to that as a dielectric material. Very, very important. A dielectric material. So a dielectric material increases the capacitance at a constant distance between the plates. You have to take note of that. So when you are talking about a dielectric material increasing capacitance, the big question is, but when a dielectric material comes and it is very thick, it's increasing the distance. No. At constant separation distance, the presence of a dielectric material will increase capacitance between the capacitors of the plate. And so it is important for you to know that a dielectric increases maximum potential difference between the plates of a capacitor, although by default, there is a decrease in potential difference. This is a very technical statement, but I'll make it clearer in this manner. First, when a dielectric material comes between the capacitor plates, it increases capacitance. That is one. Then number two, it enhances storage of charges. Number three, it decreases potential difference. Why would it decrease potential difference? Because capacitance is inversely proportional to potential difference. Remember, Q is equals to CV. The relationship between C and V is inversely proportional. So the presence of a dielectric material increases capacitance and by default decreases potential difference. But the decreased potential difference is being maximized by the dielectric material to the highest possible level. And that is the meaning of the statement that it increases possible potential difference between the plates of the capacitor. You get it? But the real fact is that it decreases potential difference. So having decreased it, the level at which it is now, it maximizes the potential. That's what we are saying. Good. So number three is that as for electric field, what happens to electric field? Electric field will drop because potential difference is directly proportional to electric field. Yeah. Remember, V is equal to ED. So if V is dropping, automatically electric field is dropping. And it's commonsensical. If you take an object and you put between two capacitor plates, the electric field between them will definitely drop. Now, what will happen to the force? The force will also drop because force is directly proportional to electric field. You get it? If you don't get it, bro, forget about it. So the next thing we're going to discuss now is the formula of a capacitor, one, in a vacuum, and two, in the presence of a dielectric. In a vacuum, the capacitance of the capacitor, or let me just give you the general formula of the capacitance of a capacitor. C is equal to KC naught. K is the dielectric constant. If there is no dielectric constant, that means it's in a vacuum. K is equal to 1. And that means the capacitance becomes the capacitor itself. But once there is a dielectric material in between, and probably the value of the constant of the dielectric material is 3, it will be 3 times the capacitance of the capacitor. If the dielectric material has a K value of 2, it will be 2 times the capacitance of the capacitor. So it will definitely increase it. And it's also important for you to note and really note that dielectric materials can either be ebonite material, mica material, or oil. Ebonite. Something is ringing in your head, right? You got to remember that. Production of charges, stuff like that. So that is that. Now, that takes us to the next aspect of this topic, and that topic is on the path of the electric field generated between the two capacitor plates of a capacitor. Of course, we did that in the previous chapter when we were discussing Gauss' law, if you remember, in a Gaussian surface, in an infinitely large plate capacitor. The electric field generated by one plate is E equals to sigma all over 2 E naught, right? 2 epsilon naught. But this time around, because capacitors are made up of 2 plates, the capacitance or the electric field generated between the capacitor plates is simply sigma all over E naught. In the presence of a dielectric material, it becomes sigma all over K E naught. That's epsilon naught. That is the dielectric constant. And on that note, you can actually calculate the relationship between E naught, which is electric field in a vacuum, and electric field in a medium. Or let me say electric field in free space and electric field in a medium. If E naught is equal to sigma all over E naught, that means in vacuum now, or free space. In the presence of a dielectric, E becomes sigma all over K epsilon naught. You can just decide to make Ke the subject of the formula where there is a dielectric constant. You now have sigma all over E naught, which is common to both of them. And when you equate them together, you will have K to be equals to E naught all over E. That means the constant becomes the ratio of the electric field in free space all over the electric field in a medium. That is what we're trying to say. Good. Now that takes us to induced charge density in a capacitor containing a dielectric material. Good. The capacitor that contains a dielectric material has what we call induced charge density, which is given by sigma in bracket 1 minus 1 all over K close the bracket. The induced charge density is sigma bracket 1 minus 1 all over K. K there is the dielectric constant of the material. And the bigger the dielectric constant, if the dielectric constant is very big, then at that point, 1 all over K will be 0. And when 1 all over K turns to 0, the induced charge density becomes equal to the normal charge density of the capacitor. So you have to be very careful with this formula because you will always need them in one way or the other. And then also, because C is equal to Q over V, that simply means that capacitance is inversely proportional to potential difference. So you can be given questions where you have first capacitance, second capacitance, first potential difference, second potential difference. So because it's an inverse proportionality, C1V1 equals C2V2. This is not dilution formula where you talk about concentration, initial concentration and initial volume, final concentration, final volume. That's not what we're talking about here. So don't have interference in your head. So this is just an inverse proportionality between capacitance and voltage, right? Good. Also take note, the thickness of a dielectric material is always equal to the separation distance between the capacitor plates, because they can give you a dielectric material having a length of this, having a breadth of this, having a thickness of this. Just know that the thickness is equivalent to the separation distance, and the length, the breadth, and the thickness, the length and the breadth will help you calculate the area of the plate, because the breadth of that dielectric material and the length of that dielectric material is equivalent to the area of the plate. So you can always do your mathematics and then get yourself safe from that dilemma, as the case may be. Then also take note, the internal resistance of a voltmeter connected across the terminals of a capacitor for a period of t seconds is given by the relationship V equals V naught e raised to the power of minus T divided by CR. That means final voltage is equal to the initial voltage epsilon, not really epsilon now, exponential, raised to the power of minus T all over CR. What does that values or those parameters represent? V naught is the initial voltage, V is the final voltage, T is the time, C is the capacitance, R is the resistance. Now this knowledge or this concept is also applicable to current and quantity of charge. So you can have Q equals Q naught e raised to the power minus T all over CR, or I equals I naught e raised to the power minus T all over CR. At times you'll be asked to calculate the resistance. So just make resistance the subject of the formula. And then you have T divided by C ln V naught over V. You got it? If you don't get it, you got to forget about it. Then the next thing we are going to talk about is capacitors being connected in a series and then disconnected. Not really connected in series or disconnected. Just take note. When a capacitor is charged in air by a potential difference V naught, then disconnected and connected to another capacitor with a dielectric material, such that the common potential difference between them, because they are now in parallel, is equal to V naught. Then it's important for you to know that the relationship between the air plate capacitor and the dielectric plate capacitor is given by V naught equals V1 bracket 1 plus K. Now the big question is, how did you get there? First, a capacitor is being charged, disconnected, and connected with another capacitor. What does that tell you? Whenever you hear that a capacitor is charged, disconnected, and connected again, the connection is usually in parallel. Okay? Never in series. Don't even think about series, because if you do, that's the beginning of failure. So it is always in parallel. Now that it was initially CV, and then finally it became CV plus KCV. Now, why is it KCV? It is KCV now because the new capacitor came with a dielectric material. So the total charge before equals the total charge after, and the total charge after becomes algebraic sum because it is in parallel. You remember? Charges in parallel are the algebraic sum. Potential difference in parallel are the algebraic. Did I say algebraic sum? Potential difference in parallel are equal. So you will now factor out the equal voltage and then solve the question as the case may be. But because there is a dielectric constant here, the C's will definitely cancel each other, because each of those C's epsilon naught A all over D. So they will cancel each other. You'll be left with V naught V1 in bracket 1 plus K. And that K is a dielectric constant. Okay? So this is sacrosanct. So you can call it the relationship between potential difference and dielectric constant in a parallel capacitor connection. So you have V naught equals V1 bracket 1 plus K, right? So the higher the value of K, the higher the final voltage, as the case may be. All right. So, and another important thing you need to note is that dielectric strength of a medium is equal to the electric field intensity of that medium. Let me just say calculate the dielectric strength of the medium. I'll be like, hey, what is dielectric strength of a medium? It is simply electric field intensity. The electric field of that medium is the dielectric strength of that medium. You get it? Then also, lastly, as far as this chapter is concerned, is that the relationship between capacitors or capacitance, area, and distance can be, likened to ideal gas equation, where you have C1 D1 all over A1 equals C2 D2 all over A2. Yes. Now you may say, but how did they come about that? It's simple. Capacitance is directly proportional to area, but inversely proportional to difference separation distance. So make K the subject of the formula, which is a constant of proportionality, and then we have CD over A. So C1 D1 over A1 equals C2 D2 over A2. Carry it. And we are done with this topic. In the next chapter, we are going to be discussing current electricity. See you when we meet again. Boom.